Okay, so hi again, and thanks everyone for the invitation. So yeah, in this talk I will present some recent results in cosmology derived from a quantum field theory of gravity based on the idea of purely virtual quanta. You can see the slide changing, right?
Yes, good.
Okay. So in particular, the outline of the talk will be this one. So I will give you a brief overview of the theory, just to give you an idea of the physical content and explain what purely virtual quantum is. Then I will present these results in cosmology that I mentioned and explain how to derive them. So we will see how to implement a purely virtual quantum in cosmology, which is a simplified version of the full quantum one. And then we will see how this idea was originated, namely in quantum field theory, to solve the problem of to reconcile renormalizability and unitarity in quantum gravity. So in the second part of the talk, we will see the full quantum theory of purely virtual quanta, so how to implement them in quantum field theory. So let's start with this brief overview, just this slide. So purely virtual quantum, also called fake particles or facon, is a degree of freedom that can mediate interactions. It can circulate inside loops of Feynman diagrams, but it cannot appear as external state in physical process. So this is the reason why we call it purely virtual quantum. So they cannot be on shell, they can only be virtual. So usually a photon can be real, either real or virtual. This kind of degrees of freedom can only be virtual. And the theory of quantum gravity with facons is a quantum field theory of a spin-2 field, massless, the graviton, a massive scalar field phi, that I will call phi, the inflaton, and a massive spin-2 facon, that I will call chi mu naught. Parameters of this theory are the mass, the Planck mass, the cosmological constant, the mass of the inflaton, and the mass of the facon. So these are the mass of the inflaton and mass of the facon. And in particular for cosmology, that will be this starting point. All the physical content is exhausted by power spectra of scalar and tensor perturbation, and in particular there are no vector perturbations. So let's start with this part and see how to introduce purely virtual quanta in cosmology. So let's start from the end. So the results of our very recent paper. So we computed the amplitude and the spectral indices for scalar and tensor perturbation that, as I said, is the physical content of this theory. We did this computation to the next to leading order in the Sitter expansion. In this table, I collect the leading order in quasi-de Sitter for the amplitudes, tensor to scalar ratio, and the spectral indices. So the black part is the same as in Starobinsky, and this red one is the modification due to the fact that there is this additional degrees of freedom, chi, the facon. So you see that the scalar parts, scalar amplitude and scalar spectral index are not modified by the presence of a facon, at least at this order, while the tensor ones are modified, all by this factor, which contains the mass of the facon and chi. We also, you can also see from this table that this order is still valid, this relation between the tensor to scalar ratio and the tensor tensor spectral index. Moreover, working out this prediction from the consistency of this approach, we derived a bound on the mass of the Facon. So consistency of the Facon approach in pure spacetime, in cosmological spacetime. We found this bound on the mass of the Facon with respect to the mass of the inflaton. So as I said, we also did the higher order correction, and these are an example. I will repeat anyway later these results. So this is the first order correction in terms of the number of e-folds for the amplitude.
Sorry, Marco, so can I ask a question? So this is typo?
What?
This M5, I mean the tensor amplitude depends on only Hubble or still inflaton mass?
Inflaton mass, yes.
Sorry, maybe I missed something. So normally tensor perturbation is determined by just how to say height of the potential. So why inflaton mass is relevant to the tensor perturbation?
So, can expand. So when you work out these results, you can do in different frameworks. I will explain later which framework we used. Usually the results are in terms of the slow roll parameter and Hubble constant. Both changes if you change the framework as expression. But they all can be written in terms of n. So if you choose to write everything in terms of n and the parameter inside the Lagrangian, these are the results. So if you're asking, in some framework, m phi is exactly the Hubble, is related to the Hubble constant, proportional.
It's just a replacement of Hubble.
Yes, depends on the framework. In some other framework, now I will show in the next slide, but in some framework they are not related.
I see. Yeah, just I wonder that. Why scalar field is Okay, sorry. Yeah, please go ahead.
This result is not dependent on the framework. So when you write everything in terms of the number of e-folds, everything is the same in any framework.
Sorry, what do you mean by framework?
Frame, yes. Einstein frame, Jordan frame.
Okay. Thank you.
Yeah, we call it framework, but maybe in cosmology it's called frame.
Okay, thank you.
I see.
Okay, so these are first part of the results, and since we have this bound and these results for the tensor to scalar ratio, we can use data from Planck. Then, for example, this. Then from this prediction, we can extract the number of e-fold from this one, which is the same as in Stravinsky inflation. And then using this bound, we can identify a range for the allowed values of the tensor to scalar ratio R. We can also plot them and see what is the region of the allowed parameters. So in this plot, we have the tensor to scalar ratio in function of the number of e-folds. These red lines is Stravinsky inflation. This blue line is the lower bound given by this bound, lower bound for the tensor to scalar ratio. These two number of e-folds are those extracted by this number. And so this colored area is the allowed range for the tensor to scalar ratio. To give some explicit number with n equals 60, you have this possibility.
Sorry, why do you impose this bound?
Yeah, I will show.
Okay.
It's coming from imposing a consistency condition to introduce Facon in pure spacetime. But this would be next. So let's start with shown the action and the property of this theory. So we work out this prediction from this action. we have the Einstein-Hilbert term, the y-squared term, and the r-squared term, which triggers inflation. So usually, if you quantize this theory in a standard way, the presence of this term, y-squared, will be responsible for the violation of unitarity or for some instability at classical level because of the presence of a so-called ghost. But what we work out in the past years is a solution to this problem, and the solution essentially is to change the quantization prescription for the degrees of freedom associated with the y-squared term. So to summarize the property of this theory, later I will give details about this. So this theory contains the graviton, the inflaton, and this massive spin 2. If the massive spin 2 is quantized with our new prescription, you can avoid to violate unitarity and keeping the contribution of this degree of freedom to renormalization at the same time. So the theory is unitary, renormalizable, and the consequence of this choice to quantize this degree of freedom in a new way is to violate microcausality, so at very small scale. And I will talk about these 3 points in the second part of the talk. Moreover, microcausality is violated, although, but macrocausality is not violated. This was shown in this paper. So for cosmology, for the moment, as usual, we choose a classical background, a cosmological one. We define the de Sitter expansion parameter, this in the usual way, epsilon and eta. Then we choose 2 frameworks. One, we call it geometric framework, is the one where everything is expressed in terms of the metric tensor. And due to the presence of this y term, we have this other mass. And since the mass of the inflaton and h in this framework are not related, the mass of the facon can be either of the order of h or of the order of the mass of the inflaton. And so when you choose this framework, you have 2 possible de Sitter expansion, both in epsilon, but in one we keep fixed the ratio between the Hubble constant and the mass of the facon, and in the other one we keep fixed the ratio between the mass of the facon and the mass of the inflaton. Then the other framework is what we call the inflaton framework, is the one where you turn the r-squared term into a scalar with a potential as usual, and this potential is the Starobinsky one.
Marco, I think the slide is cut. I cannot see everything. I don't know.
What you can see?
Probably yes. I don't know, at least in my case I cannot see the last equation. Probably it's my laptop.
I don't know.
Can you see the last equation? The other guys?
I can see last equation, S phi, G phi.
Okay,
last line is the scalar action and the potential.
Okay, probably it's my problem then, no problem.
Look, you cannot see it.
No, I don't know why. But okay, now I will try to fix. Okay, I see, it's just the action, okay, written in terms of the other frame, okay.
Okay, so I'm not giving all the details of the computation in different framework and stuff like that. I'm just giving a general idea on how to treat the degree of freedom associated to the y-squared term. Anyway, in our last paper, we did all the computation in both framework, and in the geometric framework, we did the computation in both this expansion, and of course, all the results agree, since they can be matched through a map. But let's see, so to give an idea how this works, we see for a general case. So if you study cosmological perturbation, you expand your action around some fixed background, which is time dependent usually, and and then you study the quadratic order of the action in the perturbation. So small u is a generic perturbation. Usually you end up with something like this, where you have function of time here, and you have this higher derivative term. Then you can use a field redefinition and introduce an auxiliary variable, and you can turn this higher derivative action into a two-derivative one, but with more field. And you can see, so this capital U has the correct signs, so it's a standard degree of freedom, while this V, capital V, has the opposite signs in the kinetic term. So this, if quantized with the standard method, would be a ghost. And this is the degree of freedom that we have to treat in some different way. So the procedure works this way. You start with an action for the cosmological perturbation. You do field redefinitions and introduce auxiliary variable, and you can always end up with something like this. Then when you have something like this, you solve the equation of motion for, you identify first what is the field that needs to be treated in a particular way. So in this case is V. Then you solve the equation of motion for V by means of the Fekon-Green function. In the next slide, I will explain what is a Fekon-Green function. But this fixes this unique solution for V. Then you put back the solution in the action. You get a new action that we call projected action. And then you quantize this new projected action with the standard methods.
So is the function U curvature perturbation or tensor perturbation, or just a symbolic one?
You see, this is symbolic one.
Symbolic one.
But this, in both for tensor and scalar perturbation, you can always reduce to something like this.
And the reason why second derivative appears is the presence of the wild tensor.
Yeah, yes.
I mean that U double dot appears, U double dot squared appears.
Yes. Wild tensor, and yeah, also for the tensor perturbation, also R squared introduce something like this. The scalar perturbation are all with low derivative, but they have more field. One is algebraic, you can integrate it out. So it's a bit more involved, but you always end up with something like this. From this point, is the same for all perturbation. So the operation that we did are the same. We just changed zeta, omega, and capital omega, and sigma. So this is a general procedure, given some perturbation U, cosmological perturbation U. So you end up with some new action. You quantize this new action with usual method, and then you can work out the power spectra. Remember that the physical variable is still this small u, that because of this change of variable between these two actions is a function of u, capital U and capital V. So when you want to compute the correlation function, they are still correlation function of u. And this just to say, to keep in mind this, I will repeat it later. So, so the first step of this procedure required to solve the equation of motion for the Fekon using this Fekon-Green function. So let's see what is a Fekon-Green function. So I anticipate some notion from the full quantum Fekon prescription in quantum field theory. This, as I said, the idea of this Fekon has its roots in quantum field theory, which deals with the scattering amplitude. So let's consider a usual scattering amplitude, for example, a one loop one. This is an example. So scattering amplitude is a function A of the external momenta P. And usually if you study this, if you study the analytic structure of this function as a complex function of P, of the complex variable P, you will see that there are branch points and branch cuts. So this is, for example, the case of a one loop 2-point function. when you have a complex function which has branch cuts, you need a prescription to uniquely define the function. And what is usually done in particle physics is this choice. So you need to define the function on the cut. You have multiple choices for this. You have to choose one to have a unique function. What we usually do is to define the amplitude on the cut by its analytic continuation from above the cut. This is what is usually done in particle physics. If you do that, this cut and branch point will be associated to production of particles, physical particles. And the branch points are the threshold, physical threshold. The cuts are associated to imaginary part of the amplitude. They are associated with production of this particle. While in the Facon case, instead of using this prescription, we just do the analytic continuation, this new analytic continuation that we call average continuation, because it's just the arithmetic average between the analytic continuation from above and the analytic continuation from below, above and below the cut. Now, the reason why this is a bit involved, I will give some details later. Now is just to have this idea in mind. This is what you usually do, and if you do this, you will produce particles. If you do this, then you can safely project away the degree of freedom that are associated with this cut without violating unitarity and by keeping their contribution in the normalization. And this is exactly what we wanted to do in quantum gravity. But for the moment, what is important to understand is to introduce a Facon in quantum field theory, you need to do this average at the level of the amplitude. But now we are thinking about cosmology. We just need a 3-level correlation function. So there's no loop to compute, at least at the order where we made our computations. So when you don't need to compute any loops, you can apply this average directly on the propagator, or at classical level, directly on the Green function. And so this formula translates into, in the classical limit, into a formula for the Green function. So the average, the Facon Green function, GF, is just the average between the advanced and the retarded one. So just to be clear what I mean with, so this was the first step of the procedure. To be clear what I mean with this, suppose that the Facon has an equation of motion like this one, which is the case for the cosmological perturbation, more or less. To solve this equation, you have to, where F is some external function, external force. To solve this, you have to invert this operator. The inverse is not unique. You have multiple choices, but if you fix a prescription for the Green function, then the inverse is unique, is this one. And then also the solution is unique and is given by the convolution between the Green function and the external force. So the first step of the procedure is solve the equation of motion for the Facon using this specific Green function, this average, and then put it back in the action. Now, as I said in the beginning, and maybe it's already clear from here, this is just a simplification of the general method, but for cosmology, this is enough. So it's enough just to compute this Green function, to implement this purely virtual quanta.
Excuse me, may I ask a question?
Yes.
So normally in a quadratic while plus r squared term, there's a spin 2 ghost, which you currently uses prescription to make it a Facon, correct?
Yes, exactly.
So the other degrees of freedoms, you use the usual prescriptions, and for this Facon, you use this Facon prescription. Am I understanding this correctly?
Yes, exactly.
Okay, so okay, thank you very much. I think I understand.
Okay.
So sorry, I have another question. Please go back to previous slide.
Yes.
So I'm not familiar with this prescription. So in this prescription, so what kind of initial condition correspond to this prescription?
Yeah, so if you want to solve an equation like this one in terms of Green function, usually Green function is not unique. It has some free parameters. You can fix those parameters in two ways. One way is to say, okay, this field has some initial condition, and those will fix uniquely the Green function.
Yeah.
Or in this case, because this the physics of this field, of this Facon field, is a bit different from a standard one. It's not on shell. It's not a classical field that propagates as an external state. So it doesn't have initial condition. It has to be fixed uniquely, and it's the prescription that fixes it. Now, if you want to translate this into an analogy and see what type of initial condition corresponds.
This is
This I don't know, but you should not think about as initial condition for this field, because it's something that has no initial condition. Indeed, its Green function is fixed by something that is not an initial condition. But yeah, anyway, mathematically you can try to translate it. But
I see. Okay, I see. Let me consider later. Okay, thanks.
Okay.
Marco, sorry. So at three level, this average prescription always kills any kind of homogeneous solution, right? You never have any homogeneous part in the solution of your equation.
Mm-hmm.
Because it means that you would have like homogeneous plus non-homogeneous part, right?
Yes. Yeah. Sure. So this is one. This gives you one specific solution. Yes.
Without the homogeneous. So basically, like you don't see the homogeneous contribution.
Well, you see one solution. Homogeneous depends on what is the specific solution that you choose. But yes.
Because it seems that this one is only the particular solution, right?
Yes, it's a particular solution.
Yeah, it's only a particular solution without homogeneous part.
Yes.
Okay.
Yeah, I think this solution corresponds to some particular choice of initial condition or something. So no degree of freedom. I mean, no free function, I think. Yeah.
So implicit,
I understand.
Yeah. So implicit, there is some kind of initial condition which is killing those solutions, basically.
Yeah. Homogeneous model is already fixed, I think.
Yes, mathematically you can see it as initial condition, but I would say that the interpretation is not that this field has any initial condition. Okay. So this average, anyway, let me go back a bit. This average, this is true in flat spacetime, in Minkowski spacetime, because this is derived from quantum field theory. Quantum field theory is either in flat spacetime or expanded in around flat spacetime. So the fact that this is the Facon Green function is the average between retarded and advanced is true in flat spacetime. We don't know how is it in, for example, Friedmann-Robertson-Walker spacetime. So in flat spacetime, you have to invert. You have to solve this an equation like this one, where A is a constant. Then you can use this average because we are in flat spacetime. Then you have this type of Green function. This is the solution for this. So this is the Facon Green function in flat spacetime. But we want to do that in Friedmann-Robertson-Walker spacetime. In this case, we have a similar equation to this one to find the Facon Green function. But now this A, which is this quantity, is time dependent. So it's not obvious that this is just the average, like in the flat spacetime case. This specific equation, I took it from tensor perturbation in the sitter, but they all have this form. So we don't know what is the Facon prescription in pure spacetime, but what we do know is how is the Facon Green function in flat spacetime. And there are two non-trivial cases where this, the solution of this equation has to be the flat spacetime one. One case is the conformal ultraviolet, where you have flat spacetime in conformal time. The other case is the super horizon limit, where you have flat spacetime in cosmological time. So it's enough to fix this green function to be this one in one of these two limits to fix it uniquely. And then the other one, if you choose one of these to fix one of these conditions, the other one is just a consistency check. And the solution for this is the following, which, by the way, in the sitter, this is the solution of this in the sitter, so H is constant. But having the green function, the Fekon green function in the sitter was enough for our purposes to this in this paper, and is enough to compute the power spectra to the next two leading order. So this is the green function, J are Bessel functions, and it depends on this n key, which for tensor perturbation has this form. If you change, so you do scalar perturbation or you change the framework, this changes, but the form of the equation is the same. So now you know what is the Fekon green function in the sitter, and this will be enough. So coming back to the procedure and to find the correct action to quantize. So I said you perform a change of variables in order to reach this form for the action. Then you solve the equation of motion for V using the Fekon green function. Now we know what is a Fekon green function. Then V is this solution and is a function of U. Then you put it back in the equation and you obtain the new action, which is the one that I call projected action, which is a functional of U, but in general is non-local. And so these non-localities need to be handled somehow. Luckily, thanks to the de Sitter expansion, we were able to manage this non-local term for the following reason. So this sigma, which is, let's say, the coupling between U and V, so is the term responsible for this non-local term in the action, is always, in every cases, in every perturbation, is always of order epsilon in the de Sitter parameter. This means that it's 0 in exact de Sitter, and this means also that also V is of order of epsilon, because V is this expression. And this means that the non-local term in the action is of epsilon squared order. So in our computation, either because we were in exact de Sitter or because we were stopping at some order in epsilon and the non-local term was a higher order, we were always able to neglect from the action this non-local term. And then it was much way easier to turn the projected action into the Mukhanov form. So introduce this variable V, do another change of variable, then you can express the action in this form. When you have the action in this form, you can quantize it as usual, you find the mode function, and then you extract the power spectra. As I said before, remember that the physical variable is still this small u, so from the first action I showed, that in all the cases is just a linear combination of u and v. But now v is a function of u, capital U, and capital U is related to the Mukhanov variable W. So in the end, the correlation function that we computed is this one with these substitutions.
So, sorry, please go back to previous slide. One more, please. Yes. So, if n chi squared becomes negative, what happens?
Negative, it's okay.
Yeah, it's okay.
It's not negative. Is okay. Yes.
It's not a problem.
It's imaginary that it's not okay.
Then m chi squared, we can take this kind of limit.
No, that's the next.
Okay. Next step. So this is this limit is prohibited not because this one. This is still okay.
Yes.
This is okay.
Yes, yes.
Sorry.
Wait. It
Yeah.
is n chi squared negative.
I think that from the relation you get the constraint on the mass, no?
Yes, it was what I was going to explain. So
So yeah, for me, I say the impose that has to be greater than
real.
0.
Now it has to be real.
Has to be real, yeah.
So n chi can be positive or negative, then it's okay. It can't be imaginary, which means that the square can't be negative. Yes.
Okay. Square cannot be negative. Okay, so this is not good. Then we cannot take m chi
Exactly.
the limit. Okay,
Yes.
thanks.
Exactly.
And sorry. And if n chi becomes imaginary, what happens?
Next
Just
slide.
this is next time. Okay, sorry, I wait. Thanks.
So the last thing that I wanted to explain was exactly this. So in the beginning, I mentioned that there is a bound on the mass of the Facon, and this derived from a consistency condition, which works as follows. So all the equation of motion for the Facon can be written in this way. V is the Facon, and m of t is some effective mass for the Facon, which is there because of the non-trivial background. Now, with this this prescription, the Facon prescription, works for particle, works for ghosts. So we can turn a particle into a Facon using this prescription. We can turn a ghost into a Facon using this prescription, but we cannot turn a tachyon into a ghost. So we have to impose a no tachyon condition. So the squared mass has to be positive. If you impose that around flat spacetime, you will fix the signs in the action. If you impose that, but you need to impose that also in this case, so around non-trivial background. So imposing a no tachyon condition, namely m squared, even also the squared mass, effective mass, has to be positive. So imposing this in the super horizon limit, this gives you n chi real, which is what we were saying before. You can see this also, that this is bad. If this is imaginary, is bad. You can see it also from the green function. So that green function, the more complicated one with the Bessel function, in the super horizon limit goes to the flat spacetime one, which has this form. So you see that n chi is here. So if n chi is imaginary, this sign will be an hyperbolic one. So this green function will explode somewhere, and so probably the solution. So this is the condition that we impose. You could always see that something was going bad if this was imaginary, no? But this it's also consistent with the approach that cannot be used for tachyons. So these masses has to be positive, and this is the same condition. If you impose this n chi for every cosmological perturbation, which this n chi is different if you change, if you study different perturbation, but every perturbation gives the same bound, which is the bound that I show you in the beginning. So this is the origin of this bound. So
the reason why you impose a no tachyon condition comes from the fact that if it is tachyon, B goes to diverge, and the tensor perturbation is arbitrarily large. Is this a reason?
What, can you repeat the last sentence?
I mean that if you allow the tachyon, so B can easily diverge. So in some sense, it conflicts with the tensor. I mean the bound on the tensor to scale ratio. Is this correct?
Well, it might be, yes, but the starting reason, the main point we impose this,
yes,
is because we don't know how to cure a tachyon. So our prescription, our method, this Facon method, cannot be applied to tachyon. So yes, if you want, this method cannot cure tachyon, so every bad things about tachyon will still be there.
Okay, I see.
You can always see that the same condition that we impose, just to not have tachyons, because we don't know how to treat them with this method. They cannot be treated with this method. Then it turns also reasonable from the point of view of what you said.
I see. And can I ask one more question? So now you derived this condition from the no tachyon condition. And from this bound, m chi cannot be zero, or
yes,
tachyon
exactly.
cannot be massless. And
No.
yeah, so even if you change the action, you see, now your case is in some sense some particular action, CC, while y. If you change the this term in more, how to say, generic form, massless tachyon is always prohibited or not?
Massless Facon is always prohibited. Yes.
Always prohibited.
Yes. Yeah, this will be clear later maybe, but I can anticipate you. This is because of those list of properties that I mentioned in the beginning of the theory. This theory violates microcausality, but doesn't violate macrocausality. And the fact that the violation of causality is confined in a small region of space-time is because of the mass of the Facon. If the mass of the Facon is zero, then causality is violated everywhere.
Okay, I see.
So this is even before treat cosmology. This is from quantum field theory, and not because of tachyonic behavior. This is to avoid to violate causality everywhere.
Okay, so I see. If you allow the microscale causality, massless Facon is prohibited.
Yes, but
it does not okay. It does not depend on the action or something, some particular model.
Yeah.
I see. Okay, thank you very much.
In principle, the method how to turn some degree of freedom into a Facon can be used also for massless field. There's nothing mathematically inconsistent or which is not working. It's just that then, as a physical consequence, you have violation of causality everywhere. So we want to avoid it. But mathematically, there's no problem in treating a massless field as a Facon.
Okay, thank you very much. Yeah.
That you cannot. There's no mathematics to turn a Facon into a tachyon into a Facon. That is prohibited by the theory itself. It's not done such that could work for that. But for the massless, it can work. But then you will have this consequence which you would like to avoid. So
I see. Okay, thanks.
Excuse me.
Yes.
In this Facon prescription, is the Hamiltonian bounded from below?
So the starting action, for example, in this case, is this action with the y squared, r squared, and r. But then you have to do this procedure where you project the action. So the projected action is bounded, the non-projected action is not. But then so after you applied the prescription and the Facon field are projected away, so you have to remove them from the spectrum, then yes, it's bounded.
Okay.
So to conclude this part of cosmology, I recollect again the results now that maybe it's more clear how to obtain them. So again, this is the table. The scalar parts are not modified at this order. At higher order will be modified by the mass of the Facon. Tensor is modified, and so
may I question? May I ask a question slightly? So the quantization is actually done by the one that you call the Muhanov action, right? So all of these observables are derived respect to that, correct? So also the vacuums are also take as the Bunch-Davis and the Muhanov action.
Yes.
Is there a correspondence between take like those kind of conditions with this Fakion, like in the one before you went to this Murano faction, like before you substituted the S prime U. I mean the couple slides before. So
But what is the question? Sorry,
the question is physically in this Murano form, if you quantize this, I understand that this when you quantize it, you could choose a vacuum such that it's a good vacuum, but I still don't know how this corresponds to this your previous before projected action.
It corresponds. I don't know what you mean with correspond, but so to reach this action, you have to make some change of variables. This change of variables is the one that turned the very first action into this one. First action was the one with small u. Now you have this action with the capital U and capital B. Then you have to do this operation. So everything is a function of u. Then you do another field redefinition and you get this action.
So the quantization and like choosing the vacuums are all decided in this Murano form, correct?
Yes, and then as I said in the beginning, the physical variable is still u, so you have to go back with the field redefinitions.
Okay. I think I missed that. Thank you.
Okay, so well, this is the same in without Facon. You usually to reach the Mukhanov form, you don't have it already like that, no? In the action, if you expand around perturbation, you have to redefine things, absorb terms, and then you have this form. Then you compute, you fix the Bunch-Davies vacuum, you have this solution, you have the mode function, then you go back with all the field redefinitions. The only difference here is that this field redefinition, which in the beginning involved both u and v, now involved u and v as a function of u, so it's just a function of u.
Okay, thank you. Thank you very much.
Okay, so recollecting the results. So we have this leading order behavior. You have this bound on the mass. This bound gives a window for the allowed value of the tensor to scalar ratio and can be plotted, and this is the allowed region. So let me stress this, that this theory I said in the beginning has only 4 parameters. 2 are known, the mass, Planck mass and the cosmological constant. The other 2 are the mass of the Facon and the mass of the inflaton. But now with this prediction, both are related to each other and related with Planck data. So as soon as we will have more cosmological data, the mass of the inflaton and the mass of the Facon will be fixed, and then every other prediction that we can work out from this theory would be a stringent test for the theory. So this was the first part that I wanted to present. Now we can see more detail from the theory point of view on how this Facon idea was originated. So we see purely virtual quanta in quantum field theory.
Excuse me. So in this scenario, what happens if you go backward in time, even before inflation?
What do you mean?
So you give the predictions containing n, which is the number of events, right?
Yes.
So your main concern is the period when the observable universe exceeds the Hubble horizon during the inflation. So my question is, what happens to this system if you go even before the
I don't know.
So this theory is supposed to be UV completion of gravity, quantum gravity theory.
Yes.
Okay. So this theory is supposed to successfully represent even the beginning of the universe. I'm interested in what's the consequence of this theory.
mean, Big Bang singularities, right? Something like that.
Yeah.
I don't know if this is true.
But the null energy
don't
condition
know.
is not violated.
What?
Null energy condition is not violated.
Can you repeat, please?
I think I wonder that in this theory, null energy condition is not violated. So once we go back, is it violated?
No, I don't think so. No.
Then if we go back to type in time, Haplo energy is going up and up. So unless there are some, how to say, some back reaction does not happen, or quantum gravity works very well. In any case, I think energy just blow up, no?
It might be. I don't know. I didn't address this. Certainly something to look at, but I cannot say something for sure about this. No.
I see.
You are in a de Sitter phase point.
Yes.
Deep de Sitter.
What?
This is a system which starts in de Sitter, and then there is a small perturbation, your epsilon.
Yes.
We are moving away from the Sitter point.
Yes.
And you are studying this phase.
Yes.
The deep early time, you are in more and more the Sitter phase. More
Yes.
Yes. And it's safe. It's safe.
Yes.
Yes. The Sitter H is constant, energy is constant, everything is almost constant.
Yes.
Okay.
Uh-huh.
So in this scenario, there is no beginning of the universe.
Beginning is at the Sitter phase.
Yes, exactly.
Yeah, so in some sense,
Initial
universe starts.
condition, the Sitter, almost the Sitter.
I mean, towards the past.
Or you have to ask to God.
So towards the past, the universe was eternally to Sitter. This is what you are saying.
Yeah, it starts with, as Dennis says, quasi the Sitter condition in the beginning. Yes. Okay.
I see.
So let me show this part, which might be also shed some light on why we started to introduce this and what problem we want to fix first. So the problem to be fixed, the problem that we wanted to address is the problem of renormalizability in quantum gravity. So just to remind, if you study Einstein gravity as a quantum field theory, you have this problem. The theory is unitary, which is good, as a scattering theory is unitary, but is not renormalizable. Namely, loop correction will introduce an infinite number of counter terms, which has a different form from the starting action. On the other hand, there is a theory we know since the 70s called stellar gravity from the guy that studied it for the first time, which is renormalizable but contains, as we know, ghosts, and ghosts violate unitarity. But I wanted to stress here with this that this is true only if you use the Feynman prescription, so that if you quantize everything in the standard way. But I already anticipated that by changing the quantization prescription for the ghost, you can have unitarity. So let me say something about unitarity. Unitarity is a condition on the S matrix to be a unitary matrix. The S matrix can be written in terms of its non-trivial part t, and then this unitarity equation looks like this. This is usually called optical theorem. Then, in quantum field theory, in general, we have a set of identities. They are called cutting equations. They are identities, so they are always true. They are diagrammatic identities, meaning that they are valid diagram by diagram, Feynman diagram. But if you collect them away, you collect them back, not away. Collect them back, they can be written in a compact form like this. So this resembles the unitarity equation. We call this pseudo-unitarity equation because of this H. This H in general is a diagonal matrix with ones and minus ones. And usually, if you have ghost, you have these minus ones. And these minus ones are those responsible for the violation of unitarity, because you cannot say that this equation holds if you have minus. So to have unitarity in a theory, you can have two possibilities. Either H is the identity, so the cutting equations are exactly the optical theorem, the unitarity equation, or your H is the identity in some subspace. But this cannot be done naively. You cannot just say, there is a subspace where this H is the identity, so I just project in this subspace. I just restrict my physics to be on this subspace, and then we are done. Because this is a quantum theory, and quantum correction will generate back the degree of freedom that you wanted to project away. So it will make you go out from the subspace you want to project. So if you want to do a projection, it's possible, but you cannot just say, I restrict my space on a subspace. You have to do something else. You have to do the projection has to be consistent. So this is what I say, why I call this consistent projection. So you reduce into a subspace, but you have to do something else. So in the case of Facon, this something else is changing the quantization prescription. In particular, the Facon prescription sets H to be this matrix. So if you have zeros here, as the Facon prescription does, then you can safely project into the subspace where H is the identity, and then you will have unitarity in that subspace. But at the same time, you can still have the contribution of this field that you removed in the renormalization. And this is why these fields are called purely virtual.
Marco?
Yes.
One question. From you, what happens to the ghost of gauge theories?
Yes. So the ghost of gauge theories.
With this view, yes.
In this view, the ghost of gauge theories is another type of consistent projection. It's different. It doesn't set H to be this. It does. It depends on the gauge then. In that case, instead of setting 0 straight, you have two contributions that cancels. So the effect is basically the same. You can say that Faddeev-Popov ghost doesn't propagate. You can reduce into the subspace where only the physical field propagates. So from this point of view, Facon and Faddeev-Popov ghosts are very similar from the point of view of unitarity. Of course, Faddeev-Popov ghost has no physical meaning, while this Facon leaves some remnants in the physics in the end. But from the point of view of unitarity, they are the same. And yeah, these are two possible ways to do a consistent projection. One is changing the prescription, and the other one is using the symmetries. So you can see this better from the point of view of the propagator. The propagator is an object of this form, which is not well defined as a distribution, so usually you need a prescription. So now I use a scalar propagator because everything I'm talking about is related to the analytic structure. of the propagator, so numerator doesn't really change the story. So if you have this propagator and you use the usual prescription, the Feynman prescription, and you have a plus here, or in general the residue of the propagator at the pole is positive, you have what we call a particle. If the residue is negative and you use this quantization prescription, we have what we call a ghost. This choice at the level of the propagator, so every choice that you do at the level of the propagator, the prescription that you choose, can be translated to a prescription at the level of the amplitude as a complex function. So this is what I was explaining before. So choosing this prescription for the propagator is equivalent to choose this prescription for the amplitude, so the analytic continuation from above. The Feynman propagator instead works in this way. You multiply and divide by k squared minus m squared, and then you add some fictitious mass. So this fictitious mass plays the same role of the I epsilon in Feynman prescription. You have to send it to 0 at the end. The difference is that this is not enough. You cannot just have this limit with this that goes to 0 as a distribution. You first have to integrate on some particular domain integration. So you have to deform the domain integration in the loops. After that, you do the integral, and then you can send to 0 this. But this sounds a bit involved. It is, but it's still doable. And this was the possibility of doing this was useful to prove unitarity. But in practice, it's a bit involved. You can still do that, but then you have a diagram. You have to find the right integration domain deformation. You have this complicated propagator. But what we proved in our papers is that this choice, this prescription for the propagator, is equivalent at the level of the amplitude of using this simple formula. And so we were able to prove that a theory which contains standard particles, any number you want, and phacons is unitary. Another comment that I want to make on this respect is this. So let me first go back. So the choice of this propagator is inspired by Liebig models. So Liebig had a proposal in the 70s that I'm not going to explain now, but this is inspired by them. So to having this denominator of this form, where you can have pairs of complex conjugated poles when epsilon is non-zero. So this was inspired by that theory. And I want to explain some differences between some models that you might find in the literature or some names that you can see. So let's consider a propagator like this one. Now, again, forget about the numerator because it doesn't really change the story. So suppose you have a theory with this propagator, either because it's a Liebig theory, which is a higher derivative theory with this type of propagator, and that's it, or because it's a Feynman theory, so you also have the numerator. But the denominator is always of this form. So you can have several models. So what I call Minkowski models is the one where you compute loops, amplitude. For example, this is a one loop amplitude, just the product of two propagators. When I say Minkowski models, it means that you are integrating both the energy and the space momentum on real value. So you define the theory directly on Minkowski spacetime. Besides the fact that if you do this and you quantize everything with the Feynman prescription, you have ghosts, because it's a higher derivative theory, so it's not unitary. There is also a more serious problem. This type of theory generates non-local and non-Hermitian divergences, even if the starting action is local. And this was shown in 2017 by Aglietti and Anselmi. So defining theories with this propagator, again, either because the action has this term or because you are introducing it by with your prescription, if you define it, the theory directly on Minkowski, then you have these problems, which are very bad. Then there are the Leavick models. So without going into much details, Leavick proposed to define the theories with this type of propagator by changing the integration contour for the energy and keeping on the real value the integration domain for the space moment. This way of prescribing a theory, of defining a theory, is incomplete. This is what we shown in our earliest paper. There are inconsistencies in some diagrams. This was already acknowledged by Lienbeek and Katkowski and other people. So you can find some lucky diagrams where inconsistency cancels, but in general, this doesn't give a well-defined amplitude. And it also violates Lorentz invariance. This was also shown by Nakanishi, and we also work more on this. So we found a way to complete this. So then there are the Facon models. Facon models, so I'm keeping to use this example of a one-loop diagram. Facon models, they are defined on the Euclidean spacetime. You deform both the energy domain integration and the space momenta integration domain. And in this way, you have unitarity, as I explained before. The amplitudes are not ambiguous, and they are also Lorentz invariant. So these are the three possibilities you might find in the literature, or you might ask what is the difference between what I proposed and what other people proposed. The last comment on this is that the Facon propagator is not the Cauchy principal value. So I said before, you have to take the limit of this distribution. The limit of this, in the sense of distribution, means that you have to integrate first and then perform the limit. And this is the principal value, but this is true only if you're integrating on real axis. If you change the integration contour like this limit as a distribution is not the principal value anymore. So I want to stress that you cannot do this limit at the level of the propagator, so you will get this. Because if you use this type of propagator in loop diagram, you will go back to problems similar to those found in this case, so non-local and non-Hermitian divergence. Anyway, if you don't have to compute loops, you're just doing tree-level maybe, then it's okay to use this propagator. And this is exactly what we did for cosmology. They were just tree-level. You can just do the average. So the principal value can be also written as the average between Feynman and anti-Feynman, or retarded and advanced. And this is exactly what we did with the green function before. And that was okay because it was classical level or tree level. As soon as you have to compute loops, you cannot use this. You have to use the full quantum prescription with this domain deformation. So let me give a very simple example just to see explicitly. So suppose to have a massless massless phi to the fourth theory. Now, as I said before, in principle you can use Facon prescription for massless fields. This is what I'm doing because the formulas are simpler. You will have the problem with causality, but this is just to show you how the amplitude looks like. So suppose you have this, and suppose you want to compute this diagram. Okay, you compute it, then you have this amplitude as a function of the external momentum. Then you can use the Feynman prescription or the Facon prescription at the level of the amplitude because it's much way easier. If you use the Feynman prescription, you have these results. If you use the Facon prescription, you have this one. So you can see that we have a branch point in p squared equals 0. So if p squared is negative, then this is positive, so below the threshold. This is positive, and the prescription is redundant because we have the logarithm of a positive quantity, and then the two prescriptions coincide because p squared is negative, but this is a squared, so it's okay. It's the same. If p squared is positive, then you have a negative argument of the logarithm, and you need a prescription. Feynman prescription gives you this. then this will generate an imaginary part for this amplitude. While in the case of a Facon, regardless the sign of p squared, there is a square here, this argument will always be positive and there's no imaginary part. The fact that there's no imaginary part is the crucial point that allows us to project away the degree of freedom and keeping unitarity at the same time. So as I said before, also Renaultizability is not spoiled. You can see it from here. You compute the Euclidean the Euclidean amplitude, you renormalize it, and whatever function is convergent in the Euclidean spacetime, then it's also convergent after you choose one of these two prescriptions. So the theory is still renormalizable. So to give you maybe a summary of this, let's consider the theory. Yes.
Sorry, just out of curiosity, if you go to the previous slide. So, for example, if you just have this Lagrangian as your model, you have this Lagrangian with one Facon, which is the only field. The S matrix is just the identity, right?
Exactly.
Okay.
Yeah, this is useless. It was
no, just
very,
just a curiosity.
very simple example, but it was because I wanted to show these two type of amplitude. Yes.
Okay.
After you do the projection, then the S metric is just the identity. Yes.
Thank you.
So, in the case of quantum gravity, let's see how the procedure, now is the full procedure in quantum field theory. So you have this action, and the procedure to compute scattering amplitude in Minkowski works as follows. So you first compute the amplitude in Euclidean. Amplitude is A in Euclidean spacetime. You use usual method, Feynman integrals, Feynman diagrams, and this is the same as in the standard model or the usual theories. Then this amplitude can, as they are built, they can always be decomposed into a sum of different amplitudes with only 2 branch points and 1 branch cut, like the plot that I showed you before. Then you have, for each pieces, you have different branch cut. Every branch cut is associated to the production, to some process, and the production of some degrees of freedom. If that degrees of freedom, if those degrees of freedom are the physical one, you use the prescription, the standard prescription, so the analytic continuation from above the cut. If those branch cuts are associated to a particle that you want to remove from your spectrum, like in our case is the Facon, then you use the average continuation, analytic continuation from above and below the cut. Then you project into the subspace where only the physical field lives, and then you sum back the pieces. And then you find your amplitude, which is as convergent as the one that you would obtain if you use just the Feynman prescription everywhere, but it doesn't violate unitarity. It's the projection is consistent. So this action, y squared, r squared, and the Einstein-Hilbert can be turned into an equivalent action. So I said before you can do the two frameworks. So this is I could say that this is a third framework. So it's the one when you turn both the r squared term and the y squared term into action of auxiliary field. So instead of having higher derivative, we have two derivative theory with more field. And you have explicitly the field of the scalar, that in this case is the inflaton, and then you have explicitly the field of the inflaton, which is K mu nu and is a spin 2 field. So if you do that, you end up with this action, which is made by the Einstein-Hilbert term, an action for the spin 2 field, which is a Pauli-Fierz action with the Bronx sign. This Bronx sign is a remnant of the fact that if you quantize chi using the standard prescription, then it would be a ghost. This prescription doesn't change the signs, it just changes something else. But Bronx signs are still there, plus some complicated interaction. Then you have this Starobinsky action, if you want. Then you can also couple matter, let's say a standard model, with this theory, which will couple with these fields in this way. So this was done by us in this paper, and we computed some quantities. We did several computations. We compute the absorptive part of the effective action at one loop, in particular the self-energy of the graviton. And in particular, you can resum the self-energies and find the corrected propagator for the Facon field at the pole of its mass, which has this form. So this is usual quantum field theory. When you do this, the quantity which is here is usually called gamma, and the interpretation of this quantity is the decay width. So this is the width of the Facon in this theory, which has this form, is negative. And the fact that it's negative is a signal that causality is violated, microcausality is violated. So a very short way to see it is the following. So this corrected propagator has the form of the Breit-Wigner distribution. If you do the Fourier anti-transform, you will get this. And then you see that if you trace where the gamma goes, you have gamma even also inside the theta. And so if theta is negative, if gamma is negative, this theta will pick the future instead of the past. So basically, this is the Facon-Green function. But this is suppressed because of this exponential. So you have a either because this is highly oscillating or because this is damping, then the violation of microcausality is suppressed and you have just a small violation. How small? So, as I said, this quantity is usually interpreted as the width of a particle in standard quantum field theory. In particular, its inverse is the lifetime of a particle. But now we have this new degree of freedom, the Facon, whose physics is a bit different from a standard field, a standard particle. And as I said, it can be only virtual, so you cannot really talk about its lifetime, because it doesn't behave as a standard particle. But still, you can compute this quantity, and its inverse is a time scale. So our interpretation is that this time scale is the scale where causality is violated. So how long is this violation of microcausality, how small is in time, is proportional to the lifetime. What would be the lifetime of this Facon? So just to give a number, if the mass of the Facon is 10 to 12 GeV, then this time is very, very small, and it's definitely smaller than the smallest quantity that we ever measured. Sorry, the smallest time difference that we ever measured. So our interpretation in all of this is simply that the price, if you want to call it price, but I will not, the price to pay to have both unitarity and normalizability in quantum gravity is to have this microscopic violation of causality. And the interpretation is that below certain scales, causality makes no sense. The order of the events makes no sense, and talking about time makes no sense. We don't say that, just to be clear, we don't think that at the very small scales you have absurd behavior like I don't know, scattering happening before the actual scattering happened, or I don't know, sons born before the father, or some science fiction things. We're just saying that below some scale there's no meaning in talking about causality. This is the only thing that you have to give up, which is the cheapest thing that you can abandon, because we really don't have a deep idea, a deep concept of causality at very small scale. So this is the conclusion and
Marco,
the interpretation of this. Yes.
Due to the fact that Facons are virtual, why you didn't compute the 2-point function of a true graviton, let's say graviton, no?
Mhm.
And to see there if there are violation of causality, not inside the 2-point function of the Facons.
We did. we did that computation.
Uh-huh.
It's in this paper. I didn't show it because for time reason, but no, there's no violation of microcausality there, because so let's imagine first of all, in the case of graviton,
okay, graviton is a bit complicated.
What?
No, graviton probably is too complicated. That means too many indices.
No, well, it's the same. This has two indices as well. Well, we did all the computations. We compute the self energy for everything, including any type of matter. So we have the 2-point function not only at the peak but the full one for the graviton, the inflaton, and the.
So for real particle, there is this effect? No.
For real particle?
There is this effect of presence of negative gamma?
No. Because the reason is that, okay, suppose that chi, suppose to do this computation for some real particle, let's say some scalar field or some fermion or whatever. Now you can still do this, and then this gamma for this particle that we are talking about now will depend on what is circling. For example, at one loop, what is circling inside the diagram, and it depends on the imaginary part of that diagram. So the effect of the Facon is just that if you have some contribution from diagrams where Facons are circulating inside, that imaginary part will not contribute in the gamma of this particle, but there's no negative signs.
So reality is coming from real particle only.
Yes.
And everything is safe.
And everything
is safe.
Mm-hmm.
You cannot check violation of microcausality from real particles.
No, you don't.
So why you care of
this quantity is still here.
No, okay, but the theory is self-consistent from the real point of view, from reality. In real,
yeah, but the
real particle didn't see any microcausality violations. Also for these very, very small time scales.
I think you can have some consequence of this violation, no? You can amplify it in some way, I don't know.
Now this is a point that might be good to see. We still don't know in which way we can amplify this. Again, amplify doesn't mean that really events happen before.
Yeah, I mean like consequences, not amplification. Yeah. Some consequences.
No, we also call it amplification, but the amplification of this of the fact that there is this. But if you want, I have to go back. So
you understand what I say?
Yeah.
There is no microcausality violation for real particle. If real particle is reality, no, there is no violation of microcausality. The theory is more safe than you are saying.
The fact that it might be, but the fact that this was the equation of motion for a Facon. The fact that you're using this green function,
but it's virtual.
Yes, but it enters the other interaction. The interactions between real particles are also mediated by Facons. So real particles feel the violation.
But it will be present some, let's say, instability for the propagator of real particle at higher loops or not? That means at this very small time scale, I see some violation of microcausality also in the propagator of real particles or not?
No. I mean, not in the sense. Let me go back. Not in this sense. You don't have negative.
Exactly. So if reality is coming from a real particle only, no.
But if these real particles exchange something at very, very high energies, so if they are very, very close to each other, yes, they will feel this. Because this chi mu nu is like, imagine like at CERN. At CERN you have two real particles that produce a Z boson. Imagine that they produce chi.
Sure, higher loops, but always virtual inside.
It's the exchange of something virtual, yes.
They will feel the effect of
sure.
this.
Sure,
so
but
you can,
no presence of violation. There will be some effect, but no violation of microcausality.
Yeah.
Modification, not violations. It's different.
Yeah, okay, but the modification due to what? Due to this gamma, if you want.
Sure. No, okay, but no violation.
Yes. Due to the fact that some degrees of freedom are fake instead of being real.
But modifications.
Excuse me, but you have this bright Wigner that you see in the middle here. This is a sort of green function for the mediated Facon. And you see that there is a theta function that involves the future. So you do violate, a real particle does feel the violation at very, very small distances.
Where? Sorry. So maybe I can write some here. So let me confirm. So, for example, if we consider this kind of diagram, and this is the real particle, and just simply assume that, for example, G square, phi square, Facyon square, and the Facyon is mediated. And in this case, for example, this diagram includes this imaginary part or not? Or if you prefer, for example, if you consider G phi chi squared, you see, this 2-point correlation also include this imaginary part or not?
No, if what is circling here is only chi, then there's no imaginary part.
Even for this diagram?
Yes. This gamma, the contribution of this gamma, as you can see here, they comes from everything else that circulates here, which is not a fake.
Yeah, so there I'm wondering that, so for example, for real particle, any correlation function does not include the imaginary part or vibration of the microcausality. On the other hand, only the correlation function of the Facyon has this kind of the microcausality vibration. Then, but this Facyon is not observable. So only if the correlation function of Facyon, I mean this imaginary part appears only in the correlation function Facyon, and it does not appear in the correlation function of the real particle. Maybe Dennis claims that this is not observable, and I mean nothing to do with how to say real physics or something.
But if it appears in the correlation function of the Facon, you can sandwich that correlation function between the exchange of two physical particles.
How do you write on the screen?
Just I use the Apple Pencil and share the something. I use the iPad and the Apple Pencil.
No, I don't know what I did. I did something wrong.
I think you can do with the mouse also.
Yeah, you can write mouse. Yeah, something or yeah.
How? What should I do?
You can click on that yellow.
Aha, annotate. Okay, so
Yeah.
let me
Please try. Oh, I cannot erase. No.
Okay. So this is something like this.
Yes, yes, yes.
Where this is sky and this is sky. But what we were saying is that if you have this gamma in this type of diagram, then you can also do diagrams like this, where this is sky, this is whatever, and these are physical. Then this amplitude will fill this.
Okay, I see. In this case, I see. Okay. Correlation function phi includes some imaginary part.
Yes.
I see. I see.
So, yes.
This violation is propagating in the real particle amplitude, let's say.
Yes. Yes.
Okay, good.
Very good. I see.
While is on the other hand, if you have something similar like this, now you have, let's say, physical, something else physical, bubble, something else physical. Okay. Then here inside this bubble you might have many contribution, and if one contribution is given by something that is fake, you will see the difference in this amplitude, because it will not give any contribution with the imaginary part.
I see.
So if what is circulating here, you might have many contribution. If some of them are fake, then you will see the difference. This has nothing to do now with causality. It was just a comment to say how you can see actually a physical difference between what is fake and what is not.
I see.
I have another question on this slide. I have two questions. The second question depends on the first, on the answer to the first. So let's suppose you want to do the same computation in Stellar theory, okay, without the vacuums. Okay.
Which computation?
This one of the width.
Okay.
By chi. So instead of having chi vacuum, chi ghost. Okay. In the case of Stellar theory. If you do that, I mean, you get the same, right? You get also in the case something which is negative.
Yes.
Okay. So in a way, this microscopic evaluation is not intrinsic of vacuums, but it was already there for the ghost, right? At least as in terms of this like micro evaluation small time scale. It's true that anyway with ghosts there are other problems, but so it's like that is not really intrinsic of vacuums, but it was something which is coming from the basically negative sign that there was in the ghost field, right?
Yes. So if you want the sign is negative because that thing has a negative sign somewhere in the action, and then yes. But if you ever measure something that you can relate with the existence of something like this, it will not be a ghost, because ghosts violate also unitarity.
Yes, yes.
That is for sure a completely unacceptable feature of a theory. While causality is something more fuzzy, I would say. Our comprehension of causality is not so clear, while the fact that something has to have a probabilistic interpretation because it's quantum mechanics, that is, I would say that it's more confirmed by experiments.
Yes.
So if you will see something that you can trace back to having a negative width, then it won't be a ghost, it will be a fake.
No, yes. I mean, but the computation will follow very similarly, right? I mean,
yes.
Okay. The same. Okay, thanks.
Okay, so I just had the last slide with conclusion. Then if you have other questions, we can continue. But this is not working. Okay. So conclusion to collect all the things. So we have a new theory of quantum gravity is a quantum field theory. You can extract prediction from this theory. The idea on which the theory is based on is the idea of purely virtual quanta. Thanks to them, we can have a unitary and renormalizable theory. This theory essentially is unique. It has the same computational power as the standard model, so you can just compute Feynman diagram with the usual technique. There is nothing more complicated because everything can be done after you compute the amplitude, as I explained. This theory gives prediction. One is this violation of macro causality and the difference that you might detect in scattering amplitude. And thanks to our last paper, you can also say that it's falsifiable because we compute cosmological quantities that relates all the unknown parameter of the theory in a sufficient satisfying way, such that with new data we will be able to fix all the parameters, then everything else will be a test for this theory. Okay, so that's it.
Thanks. Thank you very much. So yeah, now we have a lot of questions we had, but do you have any question or comment?
Could I ask, Marco?
Yes.
Yeah.
Sorry, it's a very basic question, so I'm sorry. So I was wondering, these virtual only these fermions, are they more of like a mathematical tool, or can we think of them as actual particles? And if so, what reason would they have for only existing virtually? Is it their very, very high mass or something else?
So they're not just mathematical, because as I explained with these last things that I drawn, you can actually see physical difference. In principle, you can see physical difference in scattering amplitude if you go to high enough energy.
Yeah.
So they're not just a mathematical thing like Faddeev-Popov ghost that you can use to have your theory, to treat better your theory, and clarifies which are the physical degrees of freedom and which are not. These are some kind in between them, because they, from the point of view of unitarity, as I said, they are like Faddeev-Popov ghost, but from the point of view of the general theory, they leave some remnants. So they are physical.
I see.
The reason why they might be, I don't know, there's no reason. I mean, it's not because they are very heavy, that's for sure, no. Whatever very heavy thing is, it can also be real, so it's not necessarily because of that. It's basically it's the only possible way to reconcile renormalizability and unitarity in quantum gravity. We did explore some other possibility, we parameterize other way to do other prescription, but there is really no room in quantum field theory to introduce new idea to cure this thing by keeping this formalism of quantum field theory, of course.
Right.
So basically, it's the only possibility, or I would say it's the only possibility.
Okay.
Then we are just left to find predictions and check if this is the reality or not.
Take on prescription is unique.
What do you mean unique?
Unique in the sense there are in principle other prescriptions which can bring to a unitary theory.
No.
It's unique.
That's what we did.
It's a theorem.
Well, yes, I would.
No. It means there are open spaces, or
I would say no. So in our first papers, where we developed this prescription, which is derived from Liebig theories. We were trying to prove that Liebig theories were wrong. Actually, we proved that they were inconsistent, and we found a way to, incomplete, and we found a way to complete them. Yeah, you can try to think about generalize the prescription, but you will find always other problem. Other problem might be, so you might have unitarity maybe, or something that is in accordance with unitarity, but then you will find non-local divergences, or you will find non-Hermitian divergences. You will find that diagrams depend on the prescription, in the sense that they depend on the fictitious parameter that you introduce. They don't cancel, or they depend on the order on which you do the limit, or there are many things that goes away on the, it's like the short, how it's called, short blanket thing, no? You cover your chest and you have your feet out. It's very constrained.
So for example, if you give up unitarity, but if you respect causality, maybe we can have another prescription.
Can you repeat?
If we give up unitarity, but we respect causality, micro-causality, then we will have some different prescription. But of course, that's a completely different theory.
Yes, I don't know. If you give up unitarity, well, first I don't see why you should.
Yeah, yeah. I change the condition usage.
That's teletheory.
Now you give up micro causality. So yeah, if we respect this one and give up this one, then maybe we have a different prescription.